Okay, so a pendulum has a period of 13 seconds on Earth. What's its period on the surface of Moon and Jupiter? Acceleration to gravity is 0.47 that on Earth. Okay, so the first thing you need is the formula for the period of a pendulum. The period of the pendulum is only dependent on two variables, the length of the pendulum and the acceleration due to gravity. The mass on the end of the pendulum, the angle that you swing it at, all those things are totally irrelevant. Again, the only thing that matters is the length of the pendulum and the acceleration due to gravity. So here, we're trying to figure out what we're trying to figure out what is the period on the surface of Jupiter where the moon. Okay, so notice what I'm trying to say is notice that we don't have the L. However, we can work backwards to get L in order to figure out the new G, right? Because you can't start solving for a G right away because you don't know L and you don't know G. But what we do know is that that the period is 13 on Earth, so we can solve for L. So I'm just going to quick do some algebra to just isolate L. So it's going to be, long story short, it's going to start to look like this. Which means that you're going to end up with t squared g over 4 pi squared equaling L. So now it's just a matter of calculation to get the L. So the t was 13, so 13 squared times 9.81 divided by 4 divided by pi squared. 41.99. So you know what? I'm just going to call this. You know what? Whatever. We'll just go 41.99. Leave it as it is. So this is pretty big pendulum, but again, the period is 13 seconds. So hey, it is what it is. Now we're going to figure out what is the acceleration. What is the period of if you take this pendulum to Jupiter. So now we're going to go back to our formula. We're taking the same pendulum, and now Jupiter is 0.47 times g. So 41.99 divided by 0.47 times 9.81, and take the square root of that, multiply it by 2, multiply that by pi, and I get 18.96. So 18.96 seconds. A simple harmonic oscillator has an amplitude of 2.6 centimeters. So what this is really saying is that, I guess I'll just draw it off to the side here, that you have this spring and mass, and it's kind of going up and down about this equilibrium point, and the max amplitude is 2.6 centimeters, which means it's going to be 2.6 centimeters up here, which means this would be the equilibrium position right there, right? So it's oscillating up and down at a max amplitude of 2.6. It says the maximum speed is 24.9 centimeters per second, and it's asking you, basically, how fast is it going when it's right here? Which, of course, is going to be the same speed it's going to be going when it's up there, just in opposite directions. So we're interested in the velocities here. And again, you don't have to solve it twice. I'm just pointing out that there are two positions where it's going to have the same velocity. Okay. So the first thing we got to understand is that the potential energy of any spring is 1/2 kx squared, where k is the spring constant. That's a measure how stiff the spring is, and x is the amount of displacement from equilibrium. Another thing we're going to have to understand is that when the spring is moving, it has kinetic energy, and the kinetic energy is equal to 1/2 mv squared. We also have to understand that the total energy of the system, so total, hold on, stickler, that the total mechanical energy is just PE plus KE. That has to be a constant, right? Energy is conserved. So we're going to take a look at this maximum speed. That will tell us the total amount of energy in the system, because at the maximum speed, by the way, the maximum speed is right here as it's going down or up, because at that point it's at equilibrium, which means that the x value is 0, which means all the potential has turned into kinetic. So we can figure. So we're just going to figure out how much total energy this system has. So 1/2 mv squared. So let's just pick out this equation and solve it. Notice that we're not given a mass, so we're just going to deal with that by leaving it as an m for right now. And it's a maximum speed of 0.249 meters per second, so 0.249 squared. Again, we are not given a mass, but I have a feeling that the masses will cancel. The m value will cancel anyways as we go through this. So 0.249 squared times 0.5, and we're going to end up with 0.031 m. Okay. And that's in joules. Not that it really matters, but I mean, at this point, but that's what we got. So the total energy of the system is 0.031 times whatever the m is. Okay. So if the maximum energy is 0.031 m, then whatever potential energy is between here, I'm just going to shade this out. Whatever the potential energy is from here to here, if you take the total amount of energy minus this potential energy right here, then whatever's left over should be your kinetic energy, right where we want it, right? So what I'm trying to say is that the entire energy of the system has to remain constant. If you could figure out the potential energy of the spring now that you've stretched it out 0.23 centimeters, and whatever's left over has to be your kinetic energy at that point, which means you can solve for the velocity. Okay, so not worrying about the m value right now, which could be a problem, but we don't know quite yet. We're going to subtract off the potential energy at this particular point. So this could be minus 1/2, and again, we don't know k, so let's just leave it in there and then deal with it once we're finished here. So let's not create more problems than we have. So 1/2 k now, the x value at this point is 0.023 squared. Whatever's left over, equals, is going to be your final velocity, the kinetic energy at that position. Okay, that's, so notice here that we have two unknowns. We have m and k. So at this point, this is kind of where you would stop and just think to yourself, is there any way that I can express either m in terms of k or k in terms of m? Right, this is where and if you can't, then you're stuck and you probably did the problem the wrong way. However, we're going to use Hooke's law. Hooke's law says that when you hang a mass from a spring, that the gravitational force downward is going to be equal and opposite to the spring force upward, and the spring force is kx. So notice, we have a relationship between m and k now. If we solve for k, it's going to be mg over x. The x is the max stretch of the spring when you put the mass on it, and whoop, boom, it's right there. It has an amplitude. That's the amplitude. That's what amplitude means. So we do have a way to get around our m and k problem. So what it will look like now is 0.031 m minus 1/2 mg all over x, 0.023 squared equals 1/2 mvf squared. This x right here is the max displacement, so 0.026. Okay. And notice that the m will go away because there's an m in every term. And if it didn't go away, then again, that's when you know you did the problem wrong. And now it is just straight up algebra. 0.031 minus this whole mess right here equals 1/2. You solve for VF. What I got when I didn't want to take the time to solve it while I'm recording, but what I get is 24.79 meters per second. Sorry, centimeters per second. So notice that it is almost, all right, it's pretty close to its max speed, but not quite. So question 3, a mass at the end of a spring. So I keep drawing pendulums. So let's just say that this is its rest position, so that would be considered your equilibrium. Now if you pull it down to, let's say, here, then it's going to oscillate from here to the same distance up, so whatever this y value is, that'll be the y value up there. That's called the amplitude again, by the way. So it's undergoing simpler harmonic motion, so it's basically just going woo, 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 like that as it goes up and down through its equilibrium and up to its maximum displacement and down to its lower maximum displacement. It's asking for at the point that it's right here, at the point it's right at its equilibrium, what is its instantaneous speed? Well, at that position, its potential energy is 0, because that would be its equilibrium position, which means that if you forget about you pulling it up and down, or you pulling it down to start with and starting it oscillating, this position is a position it would just hang at naturally, right? So that's the equilibrium position. What I'm trying to say is that that's the position where the potential energy of the spring is 0. It takes you pulling it down or lifting it up to give it potential energy to cause it to start to oscillate. So at this position right here, its potential energy is 0, which means as it oscillates, these would be positions where the velocity is the fastest. And if you think about it logically, it makes sense, right? Because, here, I'll just draw it out. So as this spring is oscillating like this, and we'll just assume that I drew these all, the amplitudes being the same, that as it passes the midpoint, it's going to start to slow down, slow down, slow down until it reaches 0. And then it's going to start to speed up, speed up, speed up until it hits equilibrium. Then it's going really fast. And then it's going to start to slow down, slow down, slow down as it goes to the top, where now the velocity is 0 again. So it's really at these equilibrium points that the kinetic energy is the fastest. So speed's at its maximum right there.